podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to do some problems. So physics problems as it relates to roller coasters. And the overarching question was, is the roller coaster safe? And we determined some numbers that make coasters safe. Any acceleration less than 4g is relatively safe. Anything above that is probably not safe. By the way, when we're done with this podcast and you have wrapped up Chapter 4, you will have done or read through some 478 pages of physics since August.
And we're half done.
And we're only halfway there. So, something to look forward to for after the holiday break. We are on page 465 doing the AP Plus. Since we're such nice guys,
We'll do number one.
We'll do number one.
Number one says a roller coaster car is traveling at 30 meters per second at the bottom of a circular loop.
Okay.
The radius of the loop is 9 meters. So I've got a speed and I've got a radius.
All right, and then in Part A it says, so this is my preliminary information. Using energy conservation, where kinetic and gravitational is constant, calculate the initial height of a roller coaster car to give it a speed of 30 meters per second at the bottom of a loop. At the highest point of the roller coaster ride, the velocity is 0. At the bottom of the loop, the roller coaster ride, the height is 0 as well. So we're looking for initial height. This is, to me, all about energy conservation. At the top, I've only got some gravitational energy.
And at the bottom, it's just giving me what I need to calculate the kinetic.
Right? So I could write down that, hey, there could be some kinetic and there could be some gravitational in the end or in the beginning, but we know that that's 0. We usually don't even write that down. mgh is half mv squared. Some of you might have panicked because no mass was given, but mass is a part of both equations, so it cancels out. We're looking for the initial height, so I'd have to divide everything by gravity, so height is v squared over 2g. Height then must be, let's see, 30 squared over 2 times 9.81, don't tell me. 900 divided by 20, help me out.
It's 100 meters per second.
No, part A, I'm sorry. We're looking for the height.
Oh, 46 meters.
46 meters. That's pretty tall. 46. That's not quite. That's not too tall. That's not quite. About 150 feet.
Right.
Nothing major there. So I now have a new value with which I can work on Part B with. So remember, speed at the bottom is 30 meters per second. Height at the top was 46 meters. Loop of roller coaster is 9 meters. What's Part B asking for?
So Part B, it says, using the equation for acceleration for centripetal acceleration, it says calculate the acceleration at the bottom.
Okay. So the centripetal acceleration is just
velocity squared
over the radius.
Correct, the radius.
So that's not terrible. So 30 squared over 9.
100 meters per second.
Squared?
Mm-hmm.
So A is 100 meters per second squared. This is roughly 10 Gs. Yikes.
That's not good.
That's not good at all.
Well, I guess it's okay if it's for a short period of time, but you get too...
Really short period.
Yeah.
The next question is not mathematical at all. It says, is this a safe acceleration? The answer to that question is obviously no.
Right.
This is the kind of acceleration that fighter pilots train for. No, not safe.
I actually put a link in the other one that showed some of the fighter pilots doing some of that G training.
With the, they have the special suits on and everything? Nice. D. At what speed would this loop with a radius of 9 meters begin to be a safety concern? So what did we say safe was? Safe was
4 Gs or 40 meters per second squared.
Okay, so safe acceleration is 4 Gs. Oh, we're going to round up just for simplicity's sake to 40 meters per second squared.
All right.
It wants to know at what speed. So the radius here is just 9.
9.
And so we are in search of safety.
Right. So that's
Centripetal acceleration is v squared over r. We're looking for the speed, AC times r, root it.
And we get 19.
So 9 times 40 root of. And you say we get
19 meters per second.
19 meters per second. That's still moving pretty fast. By the
It's 1/5 of the speed that we had before. Oh no, it's 1/5.
2/3.
Right.
So what we see here is this squared sign. We keep talking about things with squared signs and how important that squared is. So make sure that you pay attention to that just by reducing the speed by 1/3, you have now made the roller coaster safe.
So next is E. At what speed would the loop with a smaller radius of 7 begin to have safety concerns?
So the same centripetal acceleration of
40,
4 Gs or
right?
40.
And now it's velocity over 7 meters, right?
And yeah,
Velocity
it's velocity
squared, I'm
over,
sorry.
yeah, and so this is now 7. So AC is v squared over r. R times AC, root of it all. So 7 times 40 is 280. Root of 280 is?
About 17 meters per second.
So
would
by
be the
tightening
velocity.
the loop to get
You
the
gotta
same
lower the speed.
acceleration, you got to lower the speed. And your equations predict that, by the way. Next.
F. How fast would the roller coaster car be traveling at the top of the loop? So I assume this is the 7.
Mm-hmm.
Okay. How far would it be?
No, at the 9.
At the 9. At the top of the loop. Because the loop's radius is 9 and the top of the loop is 18 meters above the ground, the diameter is 18 meters. You must have an initial height of the roller coaster that you calculated to solve the above problem. So that's 46 meters, right?
Yeah, so H top was 46 meters. H at top of loop is 46 minus 18 because there's a radius and these loops are circular. So 46 minus 18, that's 28 meters. So I'm looking for the speed at the top of the loop. So it's energy conservation again. It's not quite as simple. At the top of the roller coaster is still GPE, but at the top of the loop it's GPE and it's moving, so there's some kinetic. The good news is mass still is going to go away because it's in every term. And I just need to solve for VF. So I'm going to subtract GHF from both sides. I'm going to multiply by 2 and I'm going to take the root. So if I do that, hey, there's that solution again. 2 times G times the height difference, square root of.
The one that eliminates the mass.
So 46 minus 28 is 18 times 9.81, roughly 180, times 2, roughly 360. Root of 360 is?
23. Now they used, for some reason, that is 40 meters, not 46. I don't know why that is. I see 40 meters here instead of 46. But if you use, I don't know, maybe if you use 46, it's not going to make that much of a difference, but 23 meters per second is the velocity at the top of the loop.
Right. So that's the speed at the top. Then it says, well, what's the centripetal acceleration at the top? So it just becomes that whole AC is v squared over r again. And so, once again,
Velocity now is
r is 9, velocity is now 23.
23.
It's straight plug and chug. So the centripetal acceleration is?
59 meters per second squared.
And that's roughly 6 Gs.
Right.
Is this safe?
No.
Absolutely not. So there are two safety concerns regarding accelerations in a loop. The acceleration cannot exceed 4g. This excessive acceleration would occur at the bottom of the loop, if at all. The acceleration at the top must be greater than 1g. If the acceleration required for the circular motion at the top of the loop is less than 1g, the roller coaster will leave the track and plummet to the ground. The speed at the top of the roller coaster must be large enough to require acceleration of at least 9.8 meters per second squared. So, describe if the results you found fit the safety limits in parts B through G. So the answer to that question is no.
No, right.
This is not a safe ride. Not at the top of the loop, not at the bottom of the loop. This ride has significant problems. It is important to note that, and I kind of want to do this, the other side of the safety we need centripetal acceleration to be 9.81, and on a 9-meter loop, we've got to figure out how fast you have to be going to do that. Well, the answer to that is pretty easy. You want to multiply both sides by 9. Okay, this is right around 90, and you take the square root of that to get the v, right around. And so if you're not going at least 9.5 meters per second, the car's going to have some serious problems. There's a very tight window of too low of acceleration to too high of an acceleration.
Too low and you don't make it around the turn, and too high and you crush people.
And that's why roller coasters tend to have the same features over and over again because of this window. So we just did number 1 for you. That was a lot. 2, 3, 4, and 5 are basically the same. And so I think we're going to leave you with number 6 as well.
Okay.
So I believe that wraps things up for not only the podcast, but Chapter 4 and the first semester.
Correct.
So signing off, this is Mr. White.
And Mr. Sadler.